Section 5.2, the first law of thermodynamics. Energy is neither created nor destroyed. In other words, the total energy of the universe is a constant. If the system loses energy, it must be gained by the surroundings and vice versa. The internal energy of a system is the sum of all kinetic and potential energies of all components of the system. We call this E. By definition, the change in internal energy, delta E, is the final energy of the system minus the initial energy of the system. If delta E is greater than 0, then the E final is greater than E initial. Therefore, the system absorbed energy from the surroundings. This energy change is called endergonic. As an example, we can think of the energy absorbed, or the energy that it would take to change liquid water into a gas, as is shown in the diagram. If delta E is less than 0, then E final is less than E initial, and therefore the system released energy into the surroundings. This energy change is called exergonic, and we can think of two gases in a very high energy state condensing into a liquid at a lower energy state. Changes in internal energy. When energy is exchanged between the system and the surroundings, it is exchanged as either heat, represented with a Q, or work, represented with a W. That is, the change in energy is equal to heat plus work. This table is very important. We need to know the sign conventions for heat, work, and the change in energy. For heat, a positive sign means that the system gains heat, and a negative sign means that the system loses heat. We can think of the system as a bank, and having a deposit be a positive sign and a withdrawal being a negative sign. For work, a positive sign means that work was done on the system, and a negative sign means that work was done by the system. For the change in energy, a positive sign means that the net gain of energy, there is a net gain of energy by the system, and a negative sign means that there is a net loss of energy by the system. Sample exercise 5.2, relating heat and work to changes of internal energy. Two gases, A and B, are confined in a cylinder and piston arrangement like that in figure 5.3. Substances A and B react to form a solid product, C. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves downward, and the gases react to form a solid. As the volume of the gas decreases under the constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. What is the change in the internal energy of the system? The question asks us to determine the change in energy of a system given information about heat and work. We first determine the signs of heat and work, and then use equation 5.5, which is the change in energy equals heat plus work, to calculate the change in energy. Heat is transferred from the system to the surroundings. We know this because in the question, it tells us that the system loses 1,150 joules of heat to the surroundings. So it's releasing heat, and that means that we need a negative sign for heat. Work is done on the system by the surroundings. This is told to us in the question. It says, under the constant pressure of the atmosphere, that the piston is moving downward. So because the work is being done on the system, we have a positive sign for work. This incidentally should be joules, not kilojoules. So our units are actually in agreement. Once again, this is 480 joules, not 480 kilojoules. And since we have a negative sign for heat and a positive sign for work, we wind up with a delta E value of negative 670 joules. The negative value tells us that a net quantity of 670 joules of energy has been transferred from the system to the surroundings. You can think of this change as a decrease of 670 joules in the net value of the system's energy bank account, hence the negative sign. 1,150 joules is withdrawn in the form of heat, while 480 joules is deposited in the form of work. Notice that as the volume of the gases decreases, work is being done on the system by the surroundings, resulting in a deposit of energy. For practice, calculate the change in the internal energy of the system for a process in which the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. Exchange of heat between system and surroundings. When heat is absorbed by the system from the surroundings, the process is endothermic. When heat is released by the system into the surroundings, the process is exothermic. State functions. Usually we have no way of knowing the internal energy of a system. Finding that value is simply too complex of a problem. However, we do know that the internal energy of a system is independent of the path by which the system achieved that state. In the system below, the water could have reached room temperature from either direction, starting at boiling 100 degrees Celsius or starting at freezing 0 degrees Celsius. Therefore, internal energy is called a state function. It depends only on the present state of the system, not on the path by which the system arrived at that state. And so, the change in energy depends only on the initial state and the final state, not on the path of how it got there. However, heat and work are not state functions. Whether the battery is shorted out or is discharged by running the fan, its change in energy is the same, but heat and work are different in the two cases. A battery discharged through a motor loses energy as work to make the fan turn, and also loses some energy as heat. A battery shorted out by a wire loses energy to the surroundings only as heat. No work is being performed. The value of delta E is the same for both processes, even though the values of heat and work are different from those in B.